So now that we have discussed the basic building blocks of a federated learning network, I want to discuss one very useful way to characterize a federated learning network. And this way of representing or characterizing a federated learning network facilitates the analysis a lot. So we can, using this, so this representation is called Laplacian matrix. Using this Laplacian matrix, we can often say a lot about the behavior of federated learning systems, like how long do I need to run a federated learning algorithm such that it delivers reasonably accurate model parameters or something, or how robust is a federated learning system, like if 10% of the nodes fail or 10% of the communication links are knocked out by some unintentional or intentional event, will the algorithm still work? Many of these questions can be answered by looking at the properties of a specific matrix, which is called the Laplacian matrix. And this Laplacian matrix is naturally associated with an undirected graph. So remember, each federated learning network comes with an undirected graph. This graph has undirected edges, and each edge has a weight I prime. So I prime is the edge weight for an edge between node I and I prime. And then we define the Laplacian matrix element-wise. For each edge, we have a negative off-diagonal element. So this here is an off-diagonal element of the matrix, of the Laplacian matrix. And on the main diagonal, we have the sum of all the edge weights that are connected to node I. So this is actually the weighted node degree. So if you remember the definition of the weighted node degree, this is what is here on the main diagonal for node I. So node I corresponds to the main diagonal entry I, ith column, ith row of the Laplacian matrix, and it holds the sum of all edge weights of the neighbors, so connected to the neighbors, which is exactly the weighted node degree. And zero otherwise. So if there's no edge between two nodes, I and I prime, the corresponding off-diagonal entry is zero. So this non-zero pattern, if we look at an example here for Laplacian matrix, this zero pattern captures the absence of an edge. So here in the third row, second column, there is no edge between node 2 and node 3, so there's a zero. Whereas in the second row, first column, which means between node 2 and 1, there is an edge. So that's why here is -1, because this, we assume, I need to indicate this more clearly, this is a unit weight graph. So each edge has weight 1. And in the main diagonal, we have the weighted degree. So for example, node 1 is the first main diagonal entry, has 2 edges coming out of it with unit weight, so the sum is 2. Node 2 is the second element in the main diagonal, has 1 edge with unit weight, so the degree is 1, and similar to the third node. So this is a very straightforward way to construct a matrix, to construct the Laplacian matrix for each graph. And it turns out that this Laplacian matrix has many useful properties that tell us a lot about the structure of a federated learning network. So let's start with the most obvious properties. First of all, it's symmetric. And this follows from the definition of the Laplacian matrix and the fact that the edges are undirected. So there is no direction, there's no orientation of the edges. The second very important property is that the Laplacian matrix is always positive semi-definite. So when you compute this quadratic form for any vector W with suitable dimension, so since the Laplacian matrix is n by n, where n is the number of nodes in the federated learning network, this quantity is non-negative. And this has a lot of consequences, useful consequences about the properties of this Laplacian matrix. So for any positive semi-definite property, for any positive semi-definite matrix, symmetric matrix, we have an eigenvalue decomposition, which we will discuss in a second. And moreover, what is special about this Laplacian matrix, that it is related to the variation of a vector. So let's say this vector W here carries values that are assigned to the nodes of a federated learning network. So this vector W is obtained by stacking values that we assign to each node of the federated learning network. And it turns out that this quadratic form is exactly the same as the sum over all edgewise differences. So this is a form of variation. So we call this total variation within this course, which is very nice. So a matrix algebraic construct like this quadratic form tells us something about the variation of model parameters across the federated learning network. So this already hints at the usefulness of the properties of a Laplacian matrix regarding federated learning algorithms that use this term here as a regularizer. So that's the main conceptual bridge between graph Laplacian matrix and the federated learning algorithms that we will study later on, because these federated learning algorithms use exactly this term here, or this quantity here, total variation, as a regularizer for model training. Okay, so let's continue with the properties. It gets more and more exciting. So it's not only symmetric, or because it's symmetric and positive semi-definite, it has an eigenvalue decomposition, a very distinct eigenvalue, a very nice eigenvalue decomposition. So we can write it as the sum of rank 1 matrices. So each component here in this sum is a weighted a rank 1 matrix, and the weights here, this lambda j, are the eigenvalues of the Laplacian matrix, and these vectors u superscript j are the eigenvectors, the corresponding eigenvectors of the graph Laplacian matrix. So these vectors can be chosen to be orthonormal, so we can find orthonormal eigenvectors such that this equality is valid, such that this identity holds. And it's typically very nice to work with orthonormal eigenvectors because they have zero inner product, so they don't interfere in some sense. And the eigenvalues, since it's the graph Laplacian is a positive semi-definite matrix, these eigenvalues are non-negative, so they are all larger or equal than 0. And in particular, for the graph Laplacian matrix, we know exactly that the smallest eigenvalue is 0. And you can find the eigenvector for the 0 eigenvalue by using the same the same real number for each node, because if you insert here a vector w that has the same value at each node, these differences vanish. So this becomes 0 for all edges, and this whole sum becomes 0. So there's one vector for which this quadratic form is 0, and this reflects the fact that there's one eigenvalue, there must be one eigenvalue equal to 0. And on the other end, we can upper bound these eigenvalues by the maximum node degree. So you see already here, you see also how the graph structure, the network structure by this maximum node degree is tied to the eigenvalues of the graph Laplacian matrix. So any eigenvalue is upper bounded by the 2 times the maximum node degree. Okay, so what is more, we can also read off a lot about the cluster structure from this Laplacian matrix. In particular, if the federated learning network consists of k connected components. So let's say the graph splits into k components, and there's no connection between any of these 2 different components, but each component itself is connected. Then it turns out that there's not only one eigenvalue equal to 0 in this ordered list of eigenvalues, but there are k. Exactly the number of connected components is also the number of ordered eigenvalues equal to 0. That is quite interesting. So we can read off this, let's call it dimensionality of the zero eigenvalue. So in mathematical terms, this is the geometric multiplicity of this eigenvalue is equal to the number of components in this federated learning network. And we can also characterize each component, or we can identify each component by an eigenvector. So we can find eigenvectors for this zero eigenvalue, which are exactly the indicators, the indicator functions for this class, for this component. So for each of these eigenvalues, we can construct an eigenvector that is 0 for all nodes not in the corresponding component, and non-zero only for the nodes in this component. So this is quite interesting when we want to find clusters, because if we would know this indicator function, we can find all the nodes that belong to the same cluster simply by testing is this the corresponding entry of this vector for a node, is it 0, which means it doesn't belong to the cluster, or is it not 0, which means it belongs to the cluster. So this is the basic idea behind spectral clustering, spectral graph clustering methods. They use these eigenvectors. They try to find these eigenvectors, to construct these eigenvectors that basically tell us what the clusters are in the network. And an important consequence of this property is that I want to highlight that this lambda 2, this second eigenvalue in this ordered list of eigenvalues according to their multiplicities. So there might be several eigenvalues having the same name, but they are accounted for several times depending on their multiplicity. And if the second entry, the second eigenvalue in this list is larger than 0, if and only if this second eigenvalue is larger than 0, the entire graph is connected. So we find a path between any pair of nodes. However, if this second eigenvalue is also 0, this means that the whole network splits into at least into two different components that are not connected. So it's disconnected. So this is one beautiful result of spectral graph theory. So an undirected graph is connected if and only if this second eigenvalue, second smallest eigenvalue, lambda 2, is larger than 0. Okay,